think you've heard most of them. But let me just go over the couple that I wanted to put on Screencast-O-Matic. Let's just quickly go over what's happening from now till the end of the term, which is very close, okay? We have regular class today, just like always, continuing 5.2 as far as we can get. On Wednesday, we're going to have review day. So your sheets that I gave you at the first of the term, that are near the first of the term, that had the sample questions for the final exam, multiple choice and short answer. You be going through those that we've already done. If you can't remember how to do those, we can do those. But if you can do those, let's not spend time doing something we already know. Let's focus on things we either haven't covered or you can't remember how to do. So that will be Wednesday. Now, Monday of next week, 1 week from today, technically our final exam is scheduled at 8 to 9:50, not 9:15, 9:50, okay, an hour and 50 minutes. Typically for a class like this, Math 100, I usually give you the option of having another review session on those review sheets, and then anytime later that morning, that day, Tuesday, Wednesday, or Thursday, you can take your final, okay? You can take it in 2 parts if you want to, the multiple choice part and then later the short answer part. However you want to take it for the rest of the time. If you do want to take it 8 o'clock to 9:50 Monday morning, I'll let you have it. That's not said well, is it? But I will do that. I'll get someone else to proctor the test, unless everybody wants to take it and no one wants to review, then we'll have it here. But I'll get someone to proctor the test if you do want to take it 8 o'clock Monday morning. But otherwise, you can come in anytime during the week and take your test. Like I said, 1 part or 2 part. I'll be here Wednesday morning at 8. Now, if you have a final, if you have a class Monday, Wednesday at 9:30, that final may be scheduled for Wednesday at 9 to 10:50. So don't let it interfere with some other test. But that's why I said you can come take half of it and then come back later and take the other half or whatever you want to do. Okay? Does that make sense? All right. The other issue, and this is something I really want everybody to realize, how many have done the student course evaluations yet? All right, good crowd. That means some of you haven't. Those who have, how long did it take? Second? 5 minutes, 10 minutes, nothing, something like that. It's not long, it's not arduous, it's not difficult, but it is important to us. So please do the student course evaluations. Does anyone not know how to do those? How to access it, get to it, do it? All right, good deal. All right, any questions on anything we've done so far, the schedule for the rest of the term, anything else? And by the way, here's one other thing. I meant to say this, boy, big one. On Wednesday morning, I will be returning to you all the quizzes and all the tests that we've had so far. That means if you had indicated you were not finished, you need to finish before Wednesday morning at 8 o'clock, okay? Peyton's here. Okay. So if you haven't turned in, complete anything. And by the way, Wednesday is also the last day for what? Your paper, research paper. And I'm sure there's not many more to go in this class, like only 30 or so? No, not quite that many, but close. More than 20. Only two out of my biggest class have been turned in so far. I was expecting a flood this morning when I came in. So far, the gates are still closed. I don't know where the flood is. Okay. So you've got to get the papers to me. Get it to me today. Get it to me tomorrow. Get it to me Wednesday. After Wednesday, you start losing points. Okay. So please get me the paper today. Get all your quizzes and tests done. Remember, I begged you at the first of the term, don't put it off till the end of the term because you have too much pile up then. But it's your choice. Okay. So please get everything caught up by Wednesday. I'll be returning everything. Once I've returned it, I can't let you have any more time, because then there's a chance that someone could have seen the correct answers on the work that I've returned to you. So that's drop dead date. Okay. Any questions then? All right, let's move on to where we left off last time. Let's see. It's Jalen, right? Yeah. Anyone else coming since the color off? Okay. I've got that we're at the bottom of a 252, expressing radical in simplest radical form. And for the life of me, it looks like the slide set is different from the book right now. Let me go back a slide and see what we got. Ah, yes. Okay. We did those. This is where we're beginning today. All right. Did we do any of these last time? I had that we did the first two, but I can't remember if we did or not. Did we? Let's hit them anyway. Cube root of -8 cubed. Anyone got an idea what that might be? What? Cube root of -8 cubed. Oh, last week was a long time ago, wasn't it? Okay. Any help here? What does a cube root do? Or undo? Say again? A square root undoes a square. A cube root would undo a cube. Do we have a cube here? And a cube root there? Guess what our answer is? -8. Perfect. Okay. How about the fourth root of 16 to the fourth power? 16. In this case, perfect. What if that had been negative under there? Like we had a negative in there. Yeah, it would still be positive 16, not negative. Because if you have an even index, you cannot have a negative answer. All right. Now, the next little segment here is expressing a radical in simplest radical form. This is where I had it marked that we're doing because, let's see, one person's coming in, I guess. Kara. If I can find you, there you are. All right, is anyone else snuck in while I wasn't looking? Okay. Now, it says here, expressing a radical in simplest radical form. Let's apply the transitive property to some examples to lead to the next step, next very useful property. So they're going to do some examples first, then they're going to tell you why we should do it. Okay. What would be the square root of 4 times 9? It's the square root of 36, which is 6. Okay? But that also could be done, and that's exactly true. But you could have split this into the square root of 4 times the square root of 9. What's the square root of 4? 2, square root of 9. 2 times 3, 6. 2 ways to get there. Okay? 2 ways to get there. How about this one? You want to multiply that one first? Yeah, I think I would too. What would that be?
4 times 5.
Which is? 20. And if you had multiplied those together, 16 times 25 is 400. Square root of 400 is 20, just like you had here. How about this one? Cube root of 8 times 27.
I said 2 and 3.
Yes, 2 times 3, which is 6. Or if you multiplied it out, 216, and then happen to know that or have a calculator handy, the cube root of 216 is 6. Very good. How about this one? negative 8 times 27
-2.
is what?
-2.
Negative 2,
And 3.
which is negative 6. Perfect. Can you have a negative?
Yes.
When?
When it's odd.
When the index is odd. Perfect. Okay, good deal. Those were the bottom of page 252. That then leads to the property. In general, we can state the following property. They call it property 5.4. The nth root of a product is the product of the nth roots. Okay, that's it. The nth root of a product is the product of those nth roots. That's when the nth root of B and the nth root of C are real numbers, which means neither B nor C could be negative if n is even, right? That would be, then you would have a negative number here with an even root. Can't do it. So property 5.4 states that the nth root of a product is equal to the product of the nth roots. Any questions on that? It's what we were just doing. In other words, if you can split up, if you see that this is indeed a product of two numbers, it may only be one number here, but if you can see it's a product of two numbers, and either one of those numbers has an nth root that you know, pull that out and take that one. Maybe both of them don't, but if one does, go for it. Okay? Now, expressing a radical in simplest radical form. Okay, we're going to do this in pieces. I'll go and give you the whole picture first. Well, the first part of the piece is basically what I was just saying. If there is, say, a square root, or a cube root, or fourth root, or any kind of root, and you have buried in there a perfect square or perfect nth power in that square root or nth root or whatever, then you can take that out. So always, to get it in simplest form, don't have a perfect square inside a square root or a perfect cube inside a cube root. Pull that out first, okay? There's two more rules. We'll get to those just a little bit later. The definition of the nth root, along with property 5.4, which we just did, provides the basis for changing radicals to simplest radical form. The concept of simplest radical form takes on additional meaning as we encounter more complicated expressions, but for now it simply means that the radicand is not to contain any perfect powers of the index. That's what I was just saying. Inside the radical can't be buried anywhere in there. Inside a square root, a perfect square. Inside a cube root, a perfect cube. Inside a 15th root, a perfect 15th power. Okay, not that we know any 15th powers personally. Okay, so let's see what we can do with those. Let's start with the square root of 8. Do you think that's simplest? That's a pretty simple looking form to me, but is it the simplest radical form? What do you think? All right. I think I heard something, and I think I know where it came from, but I'm not absolutely certain. I've got to get my pen. It's sort of slow activating today. Not activating at all. There it goes. Okay, what kind of root is this? Square root. You don't see a 2, you understand it to be a square root. Do you see, can you imagine any perfect squares in 8? Here, if I can find you. There you are. Anyone else come in since the called roll? Any perfect squares in 8? Yeah, 4 is. So this is the same as the square root of 4 times the square root of 2, because 2 times 4 is 8, right? What is the square root of 4? 2. I don't know what the square root of 2 is, so I'm going to leave it. Square root of 2. 2 root 2. Does that make sense? All right, let's do the next one. Square root of 45. What are we looking for? Perfect squares. Is there a perfect square buried somewhere in 45? 9 times what? Square root of 5. Okay, what is the square root of 9? And times square root of 5. 5 is not a perfect square, so we leave it like that. All right, C. Cube root of 24. What are we looking for? Yeah, but what are we looking to see if 24 contains? Any perfect cubes. Does it? Now remember, I did not early in the thing say you go over here on the right, or somewhere on a piece of paper, write down numbers 1 through 10. Then square them, then cube them, then raise them to the 4th power. As many of those as you like and get sort of familiar with what they look like. Or you can bring that now. In the final exam, remember, you can't have a formula and equation sheet. But guess what? Once you sit down to take the test, if you need to, write one, okay? Get that done early if you need it. If you don't need it, don't sweat it. Any perfect cubes in 24? 8 is a perfect cube. 4 is not a perfect cube. It's a perfect square, but 8 is a perfect cube. So the cube root of 8 times what? The cube root of 3. Perfect. What's the cube root of 8? 2 times the cube root of 3. Now don't forget that index. That's so easy to forget it once you get bogged down in the problem. Be sure you keep your index. How about the cube root of 54? Does that contain any perfect cubes? And if you can't see this right off the top, let me use this as an example. Let's do it this way. The cube root of, let's break this down into prime factorization. Remember how to do that? What's the smallest prime number? 2. Will 2 go into 54? How many times? Say again? 27. Is 27 a perfect cube? I gave it away. Is 27, what's the next prime number? Will 2 go into 27? That's what I'm trying to ask. No. What's the next largest prime number? 3. Will 3 go into 27? How many times? 9. Is 9 a prime number? That's what I was trying to ask. No. What's the smallest prime number that'll go into 9? 3. 3 times what? 3. All right. Now see what we've got here. If you see this many factors of any one number, that means that's a perfect cube. 27 is a perfect cube of 3. Now, we could have done that if you had seen it right off the top, but when no one said it, do the prime factorizations. If you can get this number of factors, pull it to the outside. So that would be what on the outside? A 3 on the outside, and what stays under the house? The cube root of 2. Perfect. You see how that's done? Later, when we're doing more complicated stuff, this technique will really serve you in good stead. Okay? There'll be another few tricks you can use, but we'll hang on to that. Any questions on those? All right. Let me erase those, and we'll see how the book did them. The first one, the cube root of square root of 8, is indeed the square root of 4 times 2. That's the square root of 4 times the square root of 2. They're putting as many steps in it. If you need those steps, put them in. Okay? This is property 5.4, and the square root of 4 we know to be 2, so that's 2 root 2. Any questions? Does it make sense? Okay, how about the next one? Square root of 45. Now we could have done prime factorizations if we wanted to. That would have worked too. But y'all saw right off the top that 9 is a perfect square. It's a factor of 45, so square root of 9 times 5 is 45. Square root of 9 times the square root of 5, and that would be 3 times the square root of 5. Because 5 is not a perfect square. Okay, then when we're going to perfect cubes, the cube root of 24, y'all saw that it was 8 times 3. That's the cube root of 8 times the cube root of 3. That's the place you'll sometimes forget to put that cube in there. That's 2 times the cube root of 3. Perfect. Let's see how they did this one. Oh, they saw it automatically. If you don't see it automatically, do your prime factorization. Cube root of 27 is, okay. Cube root of 27 times 2 is cube root of 27 times the cube root of 2. Cube root of 27 is 3. 3 times the cube root of 2. Any questions? They put extra steps in, but if you like those extra steps, use them. You can take as many steps as you want, as long as they're right. Don't take any wrong steps, okay? The first step in each example is to express the radicand of the given radical as a product of two factors, one of which must be a perfect nth power other than 1. Really awkward sentence. Also observe that the radicands of the final radicals, each case the radicand cannot have a factor that is a perfect nth power other than 1. We say that these final radicals, 2 root 2, 3 root 5, 2 times the cube root of 3, 3 times the cube root of 2, are in simplest radical forms. You don't have any perfect n powers inside an nth radical. Okay? Make sense? All right. Now, it says you may vary the steps somewhat in changing to simplest radical form. The final result should be the same. So let's consider this one, the square root of 72. Can you just see that and tell you anything? Square root of 72. Say again? Okay, it's 8 times 9. 9 is a perfect square of 3, so it's 3 times the square root of 8. So how about 8? Yes, 2 times 4. So then you have Nathan here. Okay. So you can take it another step and have 3, pull that out, times the square root of 4 times the square root of 2. Square root of 4 is 2. 3 times 2 is 6 times square root of 2. Oh, and Justin's here. All right, good deal. Anyone else come in? Okay, so as they did as you did, they saw this as the square root of 9 times the square root of 8. The square root of 9 is 3. Then when they look closer at the square root of 8, hey, that's the square root of 4 times the square root of 2. That gives you 3 times 2 times the square root of 2, and that would be 6 times the square root of 2. If you had seen it right off the top, well, you could have done it this way. I wouldn't have seen, I know it was there. Square root of 4 times square root of 18. Now, that's not one I would think of right off the top, but it's certainly true. Square root of 4 is 2, but square root of 18 contains a 9, so that's 2 times square root of 9 times square root of 2, which is 2 times 3 times square root of 2, square root of 6. Here's the one, if you were really good and alert with it, notice that 36 is a factor here. Square root of 36 times 2, square root of 36 is 6 times root 2. Any way you approach this will work. Another variation for changing radicals to simplest form is the prime factor. And this is just now getting to say it. Let's do that one with 72. Square root of 72. Be the square root of, what's the smallest prime number? 2. Will it go into 72? Yes. How many times? Say again? 36 times? Yes. Will 2 go into 36? How many times? 18. Will 2 go into 18? How many times? Will 2 go into 9? What's the next largest? 3. Will 3 go into 9? 3 times 3. There's your prime factorization. Now what do we look for? Your index here is what? 2. So pair them up. There's 2 pairs. Okay? You're not playing poker. Okay, now you can pull out a 2 and pull out a 3. 2 times 3 is 6. What do you have left? The square root of 2. Actually, prime factorization sometimes is even easier when you have these really big numbers than trying think through, well, is there a 4 in there? Is there a 9 in there? Do a prime factorization, they just sort of fall out. Be sure you do it correctly. Make sense? Let's see if they did that too. Okay? Are they skipping any here? I think they just skipped example 2, didn't they? So let's go back and do example 2. All right. Example 2. What is the square root of 50? You got several tools in your belt. What you want to use? Trial and error or prime factorization? Is that good? 2 times 25, that's a very good start. Square root 2 times the square root of 25. Either one of those perfect square? Yeah, so what would that give you? 5 times the square root of 2. I hope you said right. Square root of 25 is 5. Put that in front. Square root of 2 is 2. The square root of 2. Okay, how about the b there? Seems like we may have done that one. Square root of 45. 5 times 9. Okay? Be the square root of 5 times the square root of 9. Do we know either one of those? So this will be 3 root 5. Make sense? Okay, how about the next one? The cube root of 24. Seems like we've done that one too. I'm not sure. What you got? 8 times 3. I like it. It's the cube root of 8 times the cube root of 3. What's the cube root of 8? 2 times the cube root of 3. All right, how about that D? Does this look like a candidate for prime factorization or not? Seems like we've done it, didn't we? Say again? I can't hear. I thought so. Oh, wait. I'm looking at these. I'm not looking. Yes, we had done those. Duh. You're sitting there letting me do it. Yeah, right. Thank you very much for watching out for me and making me feel like an idiot. Okay. You got your jollies today, didn't you? Okay. Now, let's see. The ones in the book. It's the cube root, 3 times the square root of 80. 3 times the square root of 80. Is that in simplest form? It already has a number in front. What might you do? Don't lose the 3. Okay, did I hear someone say a 4? 80 is 4 times what? 20. Okay, so this would be 3 times 2 times, what is the square root of 20? Is that a perfect square? No. Does it contain a perfect square? The square root of 4 times the square root of 5. Perfect. So that would be a 3, well, 3 times 2 is 6 times 2 times the square root of 5. What's 6 times 2? 12 root 5. Okay? All right. 5 root 2, 12 root 5. Got it. Now let's do the C one. The cube root of 108. How would you approach this one? You tell me. What would you do? Okay. Are you saying the square root of 20? It's a cube root here. Say again? Okay. Okay, no. I can't understand what you're saying. You're saying the cube root of 9 times the cube root of 3. Is that what you said? I'm sorry. Oh, 12. Oh, got it. I'm sorry. That's why I couldn't understand. Well, I didn't write anything, so I can still do that. Cube root of 12. Does that help you any? Or either one of those perfect cubes? No. Okay. It might still help you. You can factor those each further. This is another way to do a prime factorization, by the way. That's the cube root of 3 times the cube root of 3, right? See, I forgot to put my cube root there. What's 12? Let's factor that further. How do you factor 12? Yes, the cube root of 3 times the cube root of 4. Now this time we did the cubes. But guess what? If you have 3 of them, what does that give you? And what does that bring outside? 3. 3 times the cube root of 4. Perfect. So you see, that's not a bad way to go either. I do the prime factorization one way. This is just another way to do a prime factorization. Okay? I usually don't write the cube roots that many times. I just do the factorization of the number. The cube root of 9 times 12, 9 times 3 times 3, 12 is 3 times 2 times 2, and that would give it to you. But you can write them as cube roots either way. Make sense? Is this the answer they got? 3 times the cube root of 4. Very good. They got it right. Excellent. Now, any questions on those? Right here? This one here? Okay. 3 times square root of 80. Is that the one you're talking about? Okay. Now, what's the question then? Right here? Okay. We did this, that 80. Someone told me 4 is a perfect square that's hiding in 80, right? That'd be 4 times 20, right? Square root of 4 times square root of 20. What is the square root of 4? 2. So they bring that down. 3 times 2 is 6. But then we looked at 20 and saw that's the square root of 4 times 5, square root of 5. Well, that square root of 4 is again a 2, right? So that would then be 6 times 2. That would be 12. The root 5 are perfect squares in there. Does that answer your question? Okay. Excellent. Okay. Now, I think, oh yeah, we've already done that, so let's just page through this. Yes, 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 yes. And that, and that. Now we're doing these. Okay, another property of nth roots is demonstrated by these examples. What do you reckon the square root of 36 over 9 is? Is that right? What? 4, exactly. What's the square root of 4? 2. But then we can notice something else. Square root of 36 is 6. Square root of 9 is 3. That'd be 6 over 3. What's 6 over 3? 2. So there's multiple ways to get there. You don't have to go to the interstate to get to Birmingham. Okay. How about this one? The cube root of 64 over 8. Either way. That would be the cube root of 8. What's the cube root of 8? 2. Very good. But what's the cube root of 64? Do I know that? 4. Yes. Cube root of 8? 2. So that's 4 over 2, and that's also 2. Okay. Sometimes these work nicely, and sometimes they don't. Okay? What's the cube root of negative 8 over 64? What would that be? Say again? Negative 1/2. Negative 8 over 64 is negative 1/8, right? You can reduce the fraction. negative 1/8, the cube root of that would be negative 1/2. Perfect. Or you could have done the cube root of negative 8, which is cube root of negative 8 is negative 2. Cube root of 64 is, you've already told me, 4. Negative 2 over 4 is also negative 1/2. So here's another, you have choices, okay? If it helps to divide first or simplify first, then take a cube root, do it. But if it's easier to see, to split them up and then do square roots or cube roots later, you can do that either, okay? Here's the general rule for that. In general, we can state this property. The nth root of a quotient is the quotient of the nth roots, where the nth root of b and the nth root of c have to be real numbers, and that also means c can't be 0, okay? Can't have 0 in the denominator, even under a radical, okay? And you can't take the nth root of an even root of a negative number. You can't do that still, okay? This property states the nth root of a quotient is equal to the quotient of the nth roots. Now this is leading to the next two properties for simplifying, expressing a radical in simplest form. The first one, you can't have a perfect nth power hiding in an nth root, okay? Take it out, okay? The other one is this. You don't want a denominator inside a radical, and you don't want a radical inside a denominator, okay? Those are the two things we try to clear. We'll use this technique to try to clear those. So to evaluate radicals such as this, how would you do the square root of 4/25? Yeah, square root of 24 over square root of 5, which is 2/5, exactly. Now, you can't do anything to this. You can't simplify it or anything else except split them up. The earlier ones you could. You could either divide them or simplify them first and then take the square roots. This one you have to take it that way. How about this? The cube root of 27 over 8. What would that be? 3 over 2. Perfect. Very good. Okay? To evaluate these kinds of radicals, which the numerator, denominator, and the fractional radical are perfect nth powers, you may use that to merely rely on the definition of the nth root. Boy, that's a weird sentence too. So let's do, we've already done that one 2/5. Okay. Yeah, we did both of those. Sorry. Okay. Yeah. Now, like I said, the next two rules for simplifying radical forms, you don't want denominators in the radicals, and you don't want radicals in the denominators. Keep simplifying until you can get rid of them. And sometimes you can't, so we'll get some new ways to do it. Let's do this one. The square root of 28 over 9. What would you do? Okay, and that would be the square root of 28 over the square root of 9. Okay. Okay, this contains a perfect square, so you use it both rules. Perfect square of 4 times 7. 7 is not a perfect square, so this would be 2 over 3 times the square root of 7. Make sense? This is 4. Okay, here it is. That's why I was trying to cover it. Okay, split that up, the square root of 28 over square root of 9. Square root of 28, we know what square root of 9 is 3. But let's then do our first rule, find any perfect squares in there. Yeah, there's a 4 in there times 7. Square root of 4 is 2. Square root of 7 is not a perfect square, so that would be 2 square root of 7 over 3. Now, as I said it before, this is another way to express this. The book, I think, does it most of the time this way, but if you ever see it this way, this is fine too. 2/3 times the square root of 7. Same thing. So don't think it's wrong. If you're doing those computerized homework packages, they'll tell you only one of those is right, but they're both right. You know, they just are really awkward. This one again, you first split it into cube root of 24 over cube root of 27. That's a perfect cube, so we can do that one. This one we have to work a little bit harder. What would we do with that? Say again?
Square.
Why would you square it?
4 times 6.
Okay, that is true, 4 times 6, but you were doing a cube root, not a square root. So what? 8 times 3. Cube root of 8 is a perfect cube. That would be 2 times the cube root of 3 over 3. And again, it's real easy to forget to put the index in. Don't forget to put the index in. If it has one, keep it. Does that make sense? Okay. Okay. Let's summarize some of the ideas that pertain to simplifying of radicals. Radicals is said to be in simplest radical form if the following conditions are satisfied. We've already said it. No fraction appears in the radical. Okay? I like to say no denominator inside the radical. And then no radical appears in the denominator. Yeah. No denominator in a radical, no radical in the denominator. Both of those violate the condition. And no radicand, that's inside the radical, when expressed in prime factored form, contains a factor raised to a power equal to or greater than the index. Okay. That is really an odd way to say it. It's true, absolutely true, but the better way to say it, no radicand has an nth power. If it's an nth radical, doesn't have an nth power within it. You pull those on the outside. That's what we were doing. Now they changed the wording around and make it really confusing. Okay. If you're doing prime factorization, I wouldn't write it like this. I'd write it as 2 times 2 times 2 times the square root of 5. Since this is the index of 2, pull out a pair of those, that would be 2 times the square root of 10. Okay? They seem to put an extra step in there and make it more complicated. Don't do that. Okay. I think they're skipping. Oh, no, they're not. So that leads to the next thing, rationalizing a denominator to simplify radicals. Okay? Sometimes it's not a perfect cube or perfect square in the denominator. It has a radical that's still there. How do we get it out? Now, you might ask yourself, why do we care? And frankly, today, I don't think y'all care very much because you have calculators and computers and you can just punch in the numbers and it'll do it. But back in the old days, you've never heard that before, have you? Before we had those, you did not want a radical in the denominator. Ever. Okay? I'll give you an example of that maybe right now. Let's consider an example in which neither the numerator nor the denominator of a radicand is a perfect nth power. Okay? Can we simplify that? It looks pretty simple to me, doesn't it, to you? But it's not. What's wrong with it? What rule does it violate? Yeah, there's a denominator in the radical. We don't want that. Okay? Now, here's how we go about getting out. Oh, here's why we don't like it. Okay? In the old days, before you had calculators, and it's not that long ago, people, okay? You've lived with them your whole lives. I was a sophomore in college before I saw my first calculator. It was in a physics classroom, 8 o'clock, Monday morning, first day of class, fall term, my sophomore year. Big lecture room, probably 200 students in it. And in walked 2 guys with these big old bulky things on their belts. That's how they wore them back then. Big old box on their belts. And the rest of us gave a collective sigh. Oh no, there goes the curve. Okay? Because these 2 guys had these newfangled calculators. These calculators came with a cord. You had to sit near the thing you could plug it in. It wasn't a rechargeable battery. You had to sit there. It's not that funny, okay? Okay? And these calculators would add, subtract, multiply, and divide. That's all, folks. And they only cost $400. Some of them are $600. Okay? Now you can get calculators like that, freebies nowadays. You go and someone's doing a special, they'll give you a calculator like that, you know. Of course, those calculators like this are about this big, you know. These were big old boxes here with, you had to plug into the wall, okay. Huh? Okay, that's an adding machine, but yeah, that was pretty close. Not quite that big. These looked about like the face of your calculator, but the boxes were about that thick, okay? And you had to plug them in. The old Hewlett-Packard, and when they first came out with them, oh, and by the way, the notation on them, if you're multiplying, you entered the first number, then entered the second number, then hit the times key. Okay, it was weird, okay. But the rest of us, of course, had on our belts slide rules. That's how we did difficult numbers. We thought, oh no, there goes the curve. They can get it to the 15th decimal place. Well, of course, that doesn't make sense anymore. So, here's why we didn't like those. Back in the day, before you had the calculator, this would have been the square root of 2 over the square root of 3. Now, someone with a calculator, you tell me what the square root of 2 is. 1.414 something. Square root of 2, I'm sorry. Keep giving me digits. I knew the first 4, but you give me the rest of them. Boy, they slow you down, don't they? 1.414 what? 2135 623 divided by 4. Okay, sorry. That'll make a lot of difference to you. Okay. 4, you said? Okay. Do the square root of 3. Hopefully this won't take quite as long. 1.7 something. Say again? Is that all? Okay. If you were dividing that, you don't even remember how to divide, do you? Not decimal numbers. Here's what you do. 1.732051. And by the way, that's an approximate. It's not exact, okay? Divide that into 1.4142135624. Before you would do this, you would move the decimal here 1, 2, 3, 4, 5, 6 places. Move this decimal 1, 2, 3, 4, 5, 6 places. Put your decimal up here and start dividing. Not a very promising condition here. That would be probably something like a 9, and then you multiply. This is how you did it, folks. This is the only way. We didn't have calculators or computers, okay? This is how you divided rational numbers. And that was approximate because you had to round both of those. Well, actually, you didn't have a calculator to give it to you. You had to go to a table of numbers. I have a CRC index that has all the square roots and cube roots and how many other roots. Tables of these numbers usually gave you 4 digits on them. But even with 4 digits, it's a nasty, messy process. Okay? Here's what we do better. Okay? We start with this, square root of 2 times the square root of 3. It's called rationalizing the denominator. You don't want an irrational number in that denominator. They're messy to divide. So how could you make that square root of 3 a rational number? Multiply it by what? The square root of 3. But if you multiply the denominator by square root of 3, you better multiply the numerator by square root of 3. You made the numerator a little worse. It's the square root of 6 now. But what's the denominator? 3. Okay? Now I can do that division. 3 will go into someone. Now I'm pretending I went to a table and found out, but you read me what the square root of 6 is. 2 point. A little louder. 4 5 4 4 9 4 8 9 7. Okay? Watch me. 8 1. This would be 19. That would be 6. That would be 14. That would be 3. This would be 28. That would be 9. That would be 1. That would be 2. That would be 1. That would be 5 and 2. Yeah. Guess what? I can do it almost in my head. Divide those numbers out. Square root of 2/3. Do it on your calculator. And I think you'll get a number pretty close to that. Say again? I'm sorry.
What did you say for
The square root of 2/3. You even know how to put that in. Okay. Depending on your calculator, most of them will be a square root sign, open parentheses, 2 divided by 3, close parentheses equal. If you have a key that is a fraction key, you could have used that one.
So that's simplifying.
Yeah. Did you get this number?
No, I was just asking.
Oh, to simplify, multiply the denominator by itself to make it a rational number. But if you do that, you have to multiply the numerator because you're multiplying by 1. And that's it. This is the simplified form. You don't have to do this. I was just showing you equals the same. This is your answer. Square root of 6 over 3. Say again? I can't hear. Is okay, I didn't understand. This is the square root of 3 into square root of 2. You could have done it that way, but I think you get that answer, right?
8.16496.
Say again?
8.8164965.
Okay, I messed up there. Okay, 4 1 6. Okay, but you see, I was doing it real fast. If you actually did it, but it's still so much easier to do it with a rational denominator than with an irrational denominator, and this is always a round off. Okay, that's why we do it. You might ask yourself, who cares nowadays? Really, no one does, as long as they got the calculator handy. But if it died or something like that, you need an approximate answer, you can get it. Okay? The answer is square root of 6 over 3. Let's erase all this. But just to give you an idea, folks, long before calculators, World War II was. Remember? How did World War II end? Does anyone recall? What was the event, or maybe 2 events, that really brought World War II to an end? Germany had already surrendered, by the way. Japan hadn't. Say again? Yes. Hiroshima and Nagasaki, the atomic bombs. Germany had been working on those, okay? We were way behind. Fortunately, some of the brilliant German scientists, thank goodness, were Jewish, and they fled Germany and came to the U.S. and helped us get working on it. Otherwise, Germany probably would have gotten it first, and who knows what would have been. We would have all been going, how these things may be. I mean, it's really scary to think of. But when doing that, I mean, here we had things that had never been done before. You take you take radioactive material, either uranium or plutonium, uranium-235 or plutonium, I can't remember its isotope. And if you have too much of that together, you're going to have an explosion. So they had to have 2 hemispheres of that, just each of them less than the critical amount. And then what you do, you blow up an explosive on the outside of those, forcing them together. Now you reach your critical mass, and then you have the nuclear explosion. So you have a traditional bomb that forces those 2 together, and then you dip. do that required some calculation that had never been made before. I mean, no one had ever done it before. And they didn't have calculators or computers. You know what they did? Has anyone ever heard of the Manhattan Project? Part of the Manhattan Project was they hired the very best mathematicians and physicists and chemists and others and engineers from all over the country, brought them in, put them in rooms. They didn't tell them why they were doing this, but they had, say, a room full of the brightest engineers, scientists, mathematicians you could get, gave them a problem, say, calculate this. And there they were doing it on paper, and they couldn't round it on the slide rule to 2 or 3 decimal places. That wasn't good enough. They had to make sure they had it right. Otherwise, it may blow up before, all sorts of things. And by the way, you had to have the explosion happen before it hit the ground. Because if it hit the ground and then exploded, then you had the nuclear reaction. It's not as effective. They wanted the explosion to happen above ground, so it destroyed for people and buildings and everything else. So it was a really difficult mathematical problem. They had roomfuls of scientists doing these difficult calculations by hand, and once they did them, they compared the answers, and the answers that showed up the most, they hoped those were the right ones. And that's how they did it. Okay, because the chances for error were so great, and the consequences of error was even greater. So that's why they rationalized denominators. Okay, it made the whole process easier. I'm sorry, we did too much. I did too much talking. Sorry about that. All right, is it almost time? No, we've got 5 more minutes. My wife gave me her old cell phone. She got a new one, so now I have an iPhone. I know how to tell time. I don't know how to answer the phone, but I know how to tell time. Okay. Huh? Landline. No. At one time, when we had an Italian kid live with us one year, senior year of high school, she got me a flip phone because she thought I needed to be able to contact him or he contact me if she was out of town, that kind of stuff. So I had that, and she had some sort of deal for $10 a month, No, she did $100 a year. And I never spent more than $10 on it, because number one, the only time I'd call her was when I was in the grocery store and she had something on the list they didn't have it. I'd call and you couldn't get reception there. I'd say, what? I can't hear you. I'm deaf anyway. So it was useless. And she said, I'm not paying for that anymore. Get rid of your phone. So anyway, now I've got this one. So maybe one day I'll even know how to answer it. Or no, never mind. Okay, but I can't tell time. Okay. So let's see what they do. Rationalize the first, split it up and square root. See, this has a denominator in the radical. So what we do, we split it up and put a radical in the denominator. You don't want that either. Well, then we have to rationalize that denominator by multiplying by the square root of 3 over square root of 3. Square root of 3 in the denominator, rationalize that. Square root of 3 in the numerator, you just have to live with it. That's the square root of 6 over 3, just like we got. All right. We refer to that process as rationalizing the denominator. Okay? The denominator becomes a rational number, then it's easy to work with. All right, we've already done the first one. Let's do this one. The square root of 5 over the square root of 8. What would you do to simplify that? Say again? Yes, you can do something to the square root of 8. What would you do? You said multiply by it. He's a hard worker, isn't he? Yeah, it'll work. Let's do it. Multiply by the square root of 8. Square root of 8. Okay? That would give you what in the numerator? The square root of 40 over... Don't do that. What is square root of 64? 8. That's why we did it, to make it a rational number. Are we through? Say again? Yeah, how do we do the 40? It's what? 4 times 10. So that'd be the square root of 4 times the square root of 10 over 8. What's the square root of 4? 2 root 10 over 8, but then you can, 1 and 4. So that would be square root of 10 over 4. Oh, sorry about that. Okay. I was in a hurry. Okay, we're right here. You got this part? Oh, because 2 will go to 8 4 times. I simplified the fraction. Factored out common factors. Okay, let me show you a slightly easier way. Square root of 10 over 4. But let me show you a slightly easier way. Notice down here the 8 has a perfect square in it, right? That'd be the square root of 5 over, what's square root of 8? Square root of? No, I'm showing you an easier way. If you hadn't done it this way, here's another way. Not rationalize, simplify that square root of 8. That's square root of 4 times square root of 2, right? Like we did before. So this will be square root of 5 over 2 times the square root of 2. Now just multiply by the square root of 2 over square root of 2. That's all you need to do. And this gives you what? Numerator? Square root of 10. Denominator? 2 times what? Square root of 2 times square root of 2. 2. That would be square root of 10 over 4. That way you don't have to go back in. You keep the numbers smaller. That's usually easier. Now there's one more thing I want to show you because it is important. I know we're almost out of time. What if you had a denominator that was like this? Give me a radical, any radical. Square root of? Give me a number. Huh? 25, I know that. Something else. 5, how about that? Give me another radical. Oh, wait, I'll let you choose. Plus or minus? Which one you want? Plus, okay, I had it, sorry. Plus, give me another radical. 3, square root of 3. What if that was in your denominator? You had something in the numerator. How are you going to rationalize that? Let me show you. We've done it before, but in a different context. You multiply by what we call the conjugate of this. You keep the same, first the same, but then you change the sign of the second one. Okay? Square root of 5 minus the square root of 3. And what do you get when you FOIL this? 5. And when you do this, negative 3 root 5 root 3, what do you get here? Plus root 3 root 5, those add to 0. And then when you do this, what do you get? Minus 3, because the sign. So you just rationalize your denominator to be 2. Your numerator stayed the square root of 5 minus the square root of 3. Believe me, that's easier to divide than the other thing. So that's the other way you rationalize your denominator. If you just have a single radical, simplify it and do it. If you have a sum or a difference of 2 radicals or a whole number of radicals, 7 plus the square root of 3. Do it the same way. Or 3 plus the square root of 7. Do it the same way. Keep the first, change the sign of the second. That's called the conjugate. Okay. We'll pick up, bring in your sheets next time, your review sheets, and anything on those sheets, or you ask me. I'm not going to pick out things to do. You ask me what you don't know. Okay? So bring your sheets next time. And get all your tests and all your quizzes completed before Wednesday. Okay? If you didn't finish the last test, many of you didn't. Okay. Well, I may not have been sure that you wanted that gray down there. Let me find it. Okay, first test. Josh Brown. Okay, is that right you want? Okay, I'll put it in the book. Okay, couldn't tell for sure if you're going to come back or not. All right. Yes, ma'am. Second test? Okay. All right. Where is it? I took some home to grade. I don't remember if yours was in that stack or not. Let me see if it was. I haven't read. There you are. Okay. And you're going next door? Okay. You what? On the last test? Oh, you finished? Okay. All right. I didn't want to do it until I knew for sure. Okay. All right. Yes, ma'am. Sorry. Push that button twice. The bottom button. No, way in the back. Right there. That. Push it once. 1, 2. Again. There. Okay. Good. Get it out of her eyes. Okay. Let me go shut this down too, so we won't be recording everything.